right, great. Final lecture on experimental stuff. Also, of course, there's a lot of experimental stuff, and I went over many atomic levels last time. So if you want like some references where you can read about this stuff, especially with regards to Rydberg and Rydberg interactions, these are 3 reviews that I like a lot. The first one is a bit more kind of perspective, quantum computing, quantum information. The second one, more simulation, many-body physics. And the last one, can we actually switch that off also? Okay. And the last one is more really the physics behind the interactions. And so, sorry. Jamil, do you know how to switch this off? Yeah, just on the side, I think. Yeah, I think it's better. Okay. So I like these 3 reviews. These are the 3 that I always recommend. But there are many more. And those are also good ones. But these ones are like, some I like. So last lecture, there were definitely a lot of levels, and atoms have a lot of levels. So if that's the only thing you take away from that, that's already really good. And actually, all these kind of selection rules and optical pumping and readout, we only did that in order to basically identify maybe 2 levels that we would like to work with out of the many. But then, okay, what we managed was, okay, we can trap now single atoms. We put them maybe a few micrometer or 1 micrometer away from each other in these optical tweezers. But then we realized, okay, that distance is actually ginormous. Over that distance, there are no interactions when the atoms sit there in the ground state. And that's why last time we spent quite some time on these Rydberg interactions, where we now take this electron maybe from the 5s shell for rubidium and then put it maybe on the 100s shell. And okay, we did a lot of kind of levels also, but intuitively you can really think of it, okay, I have this positive nucleus, I have this electron, I put it really far away, that kind of already looks like an electrical dipole, and a pretty large one, because you go to the 100s shell, and there are a little more subtleties because, okay, the electron is, of course, spherical symmetric around the nucleus, so there's no permanent electric dipole moment, but having such a separation means that I have a lot of polarizability, so I can induce an electrical dipole if I have another one sitting there, and then I get really strong interactions, basically second-order dipole-dipole interactions, so-called van der Waals interactions. So those were the things we talked about. Here we went over the electric dipole interaction, realized no permanent electric dipole moment. And then we went into the physics, kind of, how should we think about these dipole interactions? We think about it in these pair states, these Rydberg states. And then we identified 2 regimes. One is kind of, let's say, the easier conceptually regime, where you have 2 pair states that are on resonance. And then you can have really resonant energy exchange, this dipole basically hopping around. But actually more commonly, you have this non-resonant regime, where you have these pair states, for example, both rubidium atoms up to the 100s state, so 100s here, 100s here, that is maybe energetically not exactly degenerate, but not too far away from maybe 99p here and 101p here, or maybe D or something. So that's why you're in this situation where you have 1 pair state and the second pair state that is detuned, but maybe not too far. And then in second-order perturbation, you basically get this energy shift. And this because it comes from the dipole interactions, the dipole interaction R to the 3, but now second order, so R to the 6, and we get these dipole moments squared here. And then we got this Hamiltonian that basically is just the energy shift of this pair state. I would say that looks pretty boring. It's just basically, now the interaction is just an energy shift, but actually we will see that this is super, super exciting. And this is actually what's being used in these quantum computing architectures, and also we will see in simulation. So this is where we left off. So we have this interaction shift, and just to explicitly spell it out here, this C6 coefficient is now this dipole moment AB and DC D, and these are squared over this detuning from this other pair state. And this is very typical now when I excite two atoms. What is cool about it, this coefficient is huge. This is really ginormous, really, really big. Let's give an example. Let's take rubidium, and let's imagine we are coupling both atoms to the ATS state. That's not difficult. Then the C6 coefficient would be 4 terahertz per micrometer, okay, here to the 6th power. So if we had the atoms sitting 1 micrometer away from each other, then I get an energy shift of 4 terahertz of this double Rydberg state. That's huge, and even, okay, 1 micrometer might be tough, even at, because it's such a big coefficient, even if I go maybe out to 5 micrometers, I still get an energy shift of 250 megahertz. So this is really big. So let's ask, is this useful? Are these energy shifts useful? And okay, let's go, before we go to many atoms, let's just go to 2 atoms. Let's think of these 2 atoms here, I and J. I and J, and they have some distance between R. And we are now coupling both atoms here from the ground state, somewhere, some 5s state that you initialized, to the Rydberg state. And this Rydberg state maybe could be the ATS state. And we're coupling both of them to the same Rydberg state. So what is this situation? I'm drawing here the energy scales. So I'm drawing energy independence of distance between the atoms. So okay, I have 2 atoms. Both atoms have 2 states, so I have 4 possible states. The lowest energy state should just be both atoms in the ground state, so ground state. Then, okay, the next energy level would be 1 atom in the Rydberg state and the other one in the ground state. And of course, this is degenerate. It could also be the other way around. And now I also have this state both in the Rydberg state, and here we say we get these huge energy shifts. But of course, if the atoms are very far away from each other, they don't notice each other. So if they are somewhere here, it's the same energy to go 1 level higher. But then as you get closer with the atoms, this guy is going to shift dramatically up. So this is the Rydberg state. And now imagine we are driving this system with a laser or with a light field. So we shine in some light here that is on resonance with the ground to the Rydberg transition. So this light here can excite one or the other atom to the Rydberg state with some Rabi frequency omega. And if they are far away, you can also go from the single excited manifold to the double excited Rydberg manifold with the same exact wavelength or frequency of the light. Now, as I bring the atoms closer, I can still excite here to the single excited state. But, okay, now the wavelength of the light doesn't change, so it still has the same length here and energy. I cannot excite anymore to this doubly excited Rydberg state. And this here, this is something really important. So for 2 atoms close, or sufficiently close, cannot excite this Rydberg state. And this has a name. This is called Rydberg Blockade. This one is really important. This is kind of at the, we will see at the foundation of doing 2-qubit gates and quantum computing, but it's also at the foundation of doing many-body physics. Okay, so, any questions about that? This is really maybe the most important thing about Rydberg interactions. I mean, the name is quite intuitive. Blockade just means if one atom is already in the Rydberg state, I cannot excite another atom within a certain radius. Of course, if they are maybe sitting over here, then I can excite, but if they are closer, then I cannot excite anymore. Okay, maybe this blockade radius, just to put in the numbers, of course, when you drive an atom, the harder you drive, you can think of your drive almost like having some spread here. So here, I think of it like if I drive very hard, I can also drive things that are off resonant. Basically, I'm power broadening. I have this spread of omega. So the condition for Rydberg blockade is that the energy shift, and that is, of course, C6 over now this special distance, the Rydberg blockade radius to the 6th power equals omega. This is how you can calculate this Rydberg blockade radius. And actually, this Rydberg blockade radius depends on how fast you drive. If you drive, I don't know, with gigahertz, then okay, you better be detuned more than a gigahertz. This is what this says. So you calculate the Rydberg blockade radius just as the 6th root of C6 over omega. All right, so let's use this. Let's use this and think of now the situation driving two atoms to the Rydberg state. So this is now our coupling, two atoms resonantly from the ground state to the Rydberg state. And when I say resonantly, I mean I'm resonant with one atom, but okay, if now two atoms are too close, I'm not on resonance with this Rydberg state. So the Hamiltonian for this, we're driving on resonance. Okay, there's some H bar. We have some Rabi frequency omega, and now we have coupling. Okay, I have two atoms, I and J, or 1 and 2. I'm coupling one ground state to the Rydberg state, and then plus, of course, a Hermitian conjugate. Okay, this is just the independent driving of two atoms, and now I get this interaction term, the Vij, and the interaction term shifts this Rydberg level. Okay, and now imagine the atoms are close enough. Assume Rydberg blockade. Maybe we put the atoms like a few micrometers away. So we will never be able to populate this Rydberg state. And now the question is, okay, which atom gets excited to the Rydberg state? Does the left atom get excited or does the right atom get excited? Actually, it turns out that you excite a symmetric superposition of the two atoms. So this becomes basically both atoms in the ground state, and then the upper state is the W state, which is the symmetric superposition of Rydberg ground plus ground Rydberg. And you're driving this with the same laser, but what you will find is actually that you're driving it at an enhanced Rabi frequency, and it's enhanced by the number of atoms square root. So square root omega drives now this W state. So basically your Hamiltonian now becomes, for blockade, so let's write blockade, blockade just becomes ground to the W state and square root omega plus Hermitian conjugate. So it's just you're driving a two-level system at an enhanced Rabi frequency. Yes, super.
Can I see this as a kind of Hadamard gate or stuff like that?
You can, I mean, whenever you have a two-level system and you drive it with some omega, you can do a Hadamard gate on that two-level system. Here, so you can think of it like that. The important message I want to bring here, you start with something that is two independent atoms. And when they are Rydberg blockade, then they behave like one two-level system. Like sometimes people call it a super atom. That sounds fancy, but it's just that all your dynamics are just described by coupling this ground to this W state. Yeah, and then you could do also a Hadamard gate on this two-level system too. Okay, so this, yeah, super.
It's me.
Yeah.
So this excitation to reach the Rydberg stage, it's with one photon?
How do I get to the Rydberg state?
Yeah, with one photon, because I see before excitation to Rydberg stage with 2 or 3 photons.
Yeah.
Does the blocking continue with 2 or 3 photons?
Yes. So it's an excellent question. It's a great. It's also kind of a detailed question. So here, I have a ground state, and just to make it concrete, let's say we have 5s rubidium, and I'm often when I'm talking about Rydberg state, maybe I just talked about the 80s state. So actually here already you could have said, one moment we learned about optical selection rules last time, and here you want to tell me you're going from an S state to an S state. That's actually violating optical selection rules. So that does not work. But the detail that I was kind of not telling you about, that indeed you go with a 2-photon transition up here. So you have an omega 1, and then you have an omega 2. This, and here you have some, okay, it's always delta, like some delta 2-photon detuning from this intermediate state, and here you might have a 6p state. So you're going from an S state to a P state to an S state. And the reason why kind of I shoved this all under the rug is that when this delta is large, then actually you can get just a combined Rabi frequency that's just omega 1 times omega 2 over this delta 2-photon. So it's indeed a 2-photon transition typically. You could even have a 3-photon transition if you want to make it more complicated. But in the end, you can just forget about this and just treat it like driving between the 5S and the 100S or 80S. Yeah.
Okay, thanks.
Great question. Thank you. Okay, so here I went a little bit fast between this independent 2-atom Hamiltonian and this now very easy kind of 2-level system super-atom Hamiltonian. And I went so fast because this is supposed to be homework. And it's so this is maybe our Hamiltonian 1. And the homework is just show that you get from this Hamiltonian 1, you get this Hamiltonian blockade. And okay, for that you have to assume blockade. And okay, there are multiple ways of showing it. I'm just giving you a hint how to do that. You can think of the Rydberg blockade. Basically, okay, out of your Hilbert space, you get rid of all the Rydberg things. You never get there. So you can use a projector that basically just takes out this state. And if you use this projector on this Hamiltonian 1, you should arrive at the blockade Hamiltonian. But I think it's a useful exercise just to do it. And there are multiple ways of doing it. But what you should get out is that you indeed get also this enhanced Rabi frequency. And then number 2 is, can you generalize for n blockaded atoms? So when you have n blockaded atoms, what you will find is actually that also, even though in principle I have n times 2 possible, I have 2 to the n possible states, suddenly because of the blockade, they just behave like one 2-level system, everything in the ground state, and then a symmetric superposition where one Rydberg atom is basically shared between all the atoms. This is the homework, and play a little bit with this. We will also discuss that tomorrow. Okay, so this is the homework. The outcome of the homework is that n blockaded atoms is equal to one 2-level system where you just have everything in the ground state. And here you have the W state, and the W state is just basically the symmetric superposition of this Rydberg atom shared between the atoms. Of course, you have to normalize it. And then what you will find is that this omega now becomes square root n omega. So you're driving this 2-level system enhanced with square root the number of atoms between the ground and the Rydberg state. Okay, this I haven't showed you any experimental data in some time, so let's have a look if you can observe this in the experiment. Here's an experiment. All right, here's an experiment. This is already some time ago, 2017, when I was a postdoc at Harvard. And here, exactly to your question with the 2-level driving, this is exactly here. So we are coupling atoms from the ground state to the Rydberg state via some intermediate state. But for large detuning, small delta here, we can just forget about it. And the situation is, okay, we have just a linear chain of atoms that we now all at once couple to the Rydberg state. But because we are doing rearrangement, we can put the atoms exactly where we want them. And here we played with 3 geometries. Here in blue, you see single atoms that are spaced quite far away. Here they are maybe, there should be a scale bar, but they're about like maybe 20 micrometers away. So over 20 micrometers, no interaction. So this first case up here are just independent atoms. And then the independent atoms, as you couple them, they go from the ground state to the Rydberg state, back to the ground state. You see nice Rabi oscillations here when you shine in this light. Now the second situation, 2 atoms close to each other, far away from the next group of 2. You see here we do the same experiment. Suddenly they oscillate quicker. And also, kind of important here to look at the y-axis is the single Rydberg probability. So this also goes up to 1, but it doesn't mean that both atoms get excited to the Rydberg state. It just means that we find, among the 2, we find 1 Rydberg atom. So here, only 1 gets excited to the Rydberg state, or actually the symmetric superposition gets excited. And then this last case, 3 atoms, this also goes up. And if you analyze the frequency, you see exactly the square root n behavior. Yes? Yeah, no, it's a great question. So you can So basically, how many atoms could be blockaded? So because this Rydberg interaction scales super dramatically as I go, maybe this was the 70s state. If I would go to the 100s state, probably this radius would be like, I don't know, would be like maybe this large or so. And then if you would go to 2 dimensions, you could easily blockade maybe 20 atoms or so. So the difficulty maybe in that is sometimes, because now the same thing that gives you the ginormous interactions actually makes these Rydberg atoms sensitive to electric fields. And it's kind of crazy, but when you do the calculation, you find that even inside this vacuum chamber, which is of course pretty macroscopic, maybe the nearest surface is maybe like a centimeter or 2 away. If you put on the surface a few electrons or you move a few charges away, then maybe for the 100s state, you are going to shift that state actually significantly. So you get very sensitive to electric fields. So people deal with this by either going to larger vacuum chambers or putting kind of electric field shielding into the vacuum chamber that you can go higher. But actually on the other hand, what also people find, it might seem interesting to go to the largest possible blockade radius, but on the other hand, if you do that, it actually gets super boring because everything just becomes 1, 2 level system. So you actually don't necessarily want to be in the regime. Yeah. Great question. Okay, so here you also see kind of the tool. We just have a laser beam and we have the geometry of the atoms and we change what happens dramatically. And also, you immediately kind of see the connection between Rydberg blockade and entanglement, because now if you have 2 blockaded atoms, imagine 2 blockaded atoms. Yeah.
So, how about the line width of this transition? Lifetime,
Yeah, no, it's an excellent question. So the lifetime of these Rydberg states is actually very long. It's on the order of maybe 100 microseconds. So that in principle also means that the line is extremely narrow. And if you do it right, you are always in the regime where actually here this Rabi frequency, here you see microsecond. So you do like 1 oscillation in half a microsecond. So you have a few megahertz Rabi frequency. It's actually much broader than the line width.
so the line width doesn't increase with the number of atoms.
The line width does not increase with the number of atoms. Yeah. Okay, so now if you have 2 blockaded atoms, you can just generate entanglement by doing 1 optical pi pulse. So basically what this is saying, if I stop my laser beam in this 2-atom case at the top here, then I've made an entangled state. I have made this W state of ground Rydberg plus Rydberg ground. And that works perfectly fine. Or I can make a W state of 3 atoms. And it actually works so well that, okay, people look at, okay, what is the fidelity of this entangled states? And for instance, the Andres group at Caltech, they made entanglement like that. Okay, it's not so difficult to make entanglement like that, but making really good entanglement, there are a lot of small details, and they have gotten fidelities larger than 99, I don't know what it is, 0.6%. Pretty high. So this simple energy shift, this simple Rydberg blockade can be a source of entanglement. Great. Okay, I'm not sure if I'm consistent in my numbering, but I wanted to talk a little bit, because it can get confusing for people, about qubit, or let's call it spin selections. So we have so many atoms, so many levels, and also many atoms, that there are different choices of how I could encode a qubit or how I could encode a spin. Right now, we talked about what maybe now by convention people call a ground Rydberg qubit. and replace qubit with spin if you feel more comfortable with that. And here basically we had the ground state, and we have the Rydberg state, and we can drive between them with some omega. So this could be one choice of defining a qubit. This choice is great in some sense. It's maybe the advantages of this is, or the properties is qubit states interact. Obviously, this Rydberg state interact. And maybe I call this the 1 state, and I call this the 0 state. This is how I define it. But there's like a slight, if you care, maybe a slight disadvantage that this 1 state will decay over time. It's not a ginormous disadvantage. It maybe decays on the order of 100 microseconds. So because the dynamics, as we've seen, is kind of megahertz in 100 microseconds, you can do a lot of cool physics. So this is a very typical choice for if you want to simulate spin models or something like that. Then there's a 2, and I think by convention people call this now the ground qubit. And this is more what you have in mind when you think, ooh, I want to build a quantum computer. What you do then is actually you make use of these hyperfine states here. So we have these different manifolds. And in these hyperfine states, you define one of the ground states as your 1, and the other ground state as your 0. So this is great. This is we were talking about it last time or the time before, like when I said, oh, atoms are super coherent and you can have 10 seconds coherence time. This is this encoding, qubit states, very coherent. So this is awesome, but the problem is these states don't interact. And that is, of course, a problem, but in quantum computing, people then realized I can actually use the Rydberg state not really as a qubit state, but just as a mediating state to actually get a 2-qubit gate. So this is the architecture that you might use in quantum computing, also maybe for digital quantum simulation. This is really interesting. You encode things in the hyperfine states, and you only use the Rydberg state in between when you want interactions or when you want a gate. And then number 3, people call the Rydberg qubit. And here you take several Rydberg states, and okay, you probably start in the ground state down here. This is of course the Rydberg states decay, but the advantage is now that you have flip-flop interactions. This is basically this resonant regime that we first talked about, where neighboring atoms can exchange energy. So if you want to study maybe a Heisenberg, an XY model, you would want to work in this encoding. So, but okay, there are a lot of freedoms, and what I always say is kind of the typical situation, but if you get creative, you can even maybe combine different encodings or use encodings for different things. So for quantum information processing, typical 2. So you use the ground encoding, and for, let's say, simulation, typical, you use 1 or 2. No, 3, sorry. Depending on if you want just a sigma ZZ term, as we will see, or a XY Hamiltonian. Okay, but before we go into the Hamiltonians, I wanted to say just one thing, how you can realize a 2-qubit gate. So just briefly talk about quantum information processing, and then we go into simulation. But any questions on these encodings or the interaction so far? Okay, good. So just very briefly, imagine now you are in this number 2 encoding. So you have amazing qubit states, 10-second coherence time. You have amazing single qubit gates just by shining in microwave, for example. But now the missing key ingredient is a 2-qubit gate. And for the 2-qubit gate, we use the Rydberg state. So number 5, 2-qubit gates. In our 2 encoding. And the reference is a really famous paper for this. This was like early 2000s, where you have many papers that start quantum computing with X, and then they take some molecules or quantum dots architecture, and then they realize what the 2-qubit gate in that architecture would be. So this is from Dieter Jaksch, 2000. So it's actually a long time ago, and then it took quite some time to actually realize this promise. And some people actually in the meantime got a little bit frustrated about Rydberg atoms, and they thought, oh, maybe it doesn't work. But then, okay, because we got the tweezers and the rearrangement, actually people got super excited about that. And this is now why you have also, I don't know, like 6 quantum startups working on quantum computing. But okay, the proposal was out in 2000. And the situation is exactly this situation. We have our 2-qubit states, 2 atoms, in the ground state. So we have our 1 and our 0 here, very coherent. And then we also have the Rydberg state that we just want to use to get somehow interactions. You need some kind of interaction to realize a 2-qubit gate. And we are in the situation where both atoms are blockaded. That's also a really important realization. Like you could come up with a gate design that depends exactly on the interaction strength of the 2 atoms. And that's also true for quantum simulation. You can come up with protocols that depend exactly on that. That's often very dangerous because, as we noticed last time, the atoms actually move a little bit around. So the exact number of this interaction can fluctuate, and actually fluctuate maybe by 10% or maybe even 20% depending on the temperature and on the distance. Instead, if you realize a protocol that just depends on the fact that you are blockaded, it doesn't really matter if you're more strongly blockaded, less strongly blockaded, because all of these situations, you shift away this Rydberg state. And it doesn't really depend on how much you shift it because you never populate it. You never sit there and you never pick up some random phase because the energy is not stable. So this is the situation, 2 blockaded atoms. Omega couples now just from one of these hyperfine states to the Rydberg state. That's very typical because these hyperfine states, they are maybe gigahertz away. So I can just park it on one and not on the other. And this is the situation. So think of here. And the one extra ingredient is individual addressing. And what this means is I can decide, do I only want to couple the first atom to the Rydberg state or the second atom, or maybe both at the same time. And now the 2-qubit gate is very simple. 2-qubit gate just 3 pulses. And the pulses are the following. So I'm drawing time. And I start off by doing omega 1 pulse. And I leave this pulse on exactly for the time that it takes to go from the ground state to the Rydberg state. So this is what we call a pi pulse. Then I do an omega 2 pulse. And what I do is a 2 pi pulse. So this is exactly the time it takes to go from the ground state through the Rydberg state back to the ground state. It seems first a little bit weird. It seems like nothing happened, but we will see something did happen. And then in the end, we do another pi pulse on the first atom. You realize like here on omega 1, we have a pi pulse first and then a second pi pulse. So together that's also 2 pi. Because in the end of the gate, you always want to be back in the ground state. These are your good qubit states. You never want to leave anything in the Rydberg state. You just want to use the Rydberg state to do this gate. And this is the gate. And let's see why this is a gate. I mean, there's multiple ways of convincing yourself. Sometimes I find it quite useful when you analyze a gate. You just make a little table. You look at the input states and the output states. And okay, there are just 4 states, so we can do that little exercise. This is a very easy input state, 0, 0. Both atoms sit here. And now I do the first pi pulse. It's very off-resonant. I do the second 2 pi pulse. Also nothing happens. And the last one, also nothing happens. So in this situation, just nothing happens. 0, 0 goes in and just comes out again. But now, these other states are kind of special, or they are different. They're different. Now imagine I'm in 0, 1. So this guy and this guy. Now, okay, the first pi pulse is not going to do anything. I'm off resonant. The second 2 pi pulse is actually going to take this atom on a little round trip. Does a 2 pi rotation, comes back to the 1 state. And then, okay, this last pi pulse doesn't do anything because my first atom sits here. So you could think nothing happened. I did this 2 pi little round trip. But actually, when you do a round trip like that on the Bloch sphere, of course, you come back with the same population, but you will pick up a geometric phase of pi. So it actually comes back as minus 0, 1. Next state, 1, 0. Actually, very much the same story, but now the roles are reversed. First pi pulse takes the first atom up. 2 pi pulse doesn't do anything. And the last one takes it back down, the first atom. So now the first atom did a 2 pi rotation. But okay, we look at the combined states here. So the combined state picked up a minus sign. And now comes the special thing, and this is what makes the gate actually. What happens to the 1, 1 state? The 1, 1 state, okay, we sit here and we sit here. Obviously, the first pulse takes this atom, puts it in the Rydberg state, and now this 2 pi pulse is blockaded. So this one doesn't do anything, and then I take the first atom back down to the ground state. So also this state picks up a minus sign, and this is very important. And now this is... if you look at this, so this is a gate, a 2 by 2 matrix. On the diagonal, you have 1 positive 1 and 3 negative 1s. If you do a couple more single qubit rotations, this looks exactly like 1, 1, 1, minus 1. And what this is a controlled Z gate. And this controlled phase gate, you can also turn it into a C0 gate with single qubit rotation. So this can make entanglement, and together with your single qubit operations, this gives you full quantum computing on atom arrays. So this was the cool realization in 2000. It took about until 2009 that people actually did this gate. That time this gate didn't have great fidelity yet. We didn't have the control over the tweezers, not quite like we have it now. But over time, this fidelity just went up, went up, went up. And okay, I'm not going to go into all the improvements, but there's a very cool recent highline. And this is also from the Harvard group, where they realized now a CZ gate with 99.5% fidelity. So this is, or probably this was a lower bound, but somewhere around there is the gate fidelity now. This is not exactly the gate how I describe it. They do a little bit slightly variation of it, but the idea is the same, that one of these states picks up a minus sign, so you get a C phase gain. So there's a lot of excitement because of this, that now we have very good single qubit gates, extremely coherent qubits, also really good 2-qubit gates, and the exciting prospect is, okay, I can trap maybe 1,000 atoms. So this is super cool. And this is probably the pitch, I would say, that I would make if I want to get like, I don't know, 100 million for my startup. But okay, for you, I do a different pitch. Okay, I do make the pitch. Now we have very good single qubit gates and 2-qubit gates. So we have a universal gate set. Gate set for quantum computing. And we can start to put it all together. And okay, I have a lot on this, but I'm going to skip this. My comments would be, okay, that's not completely enough yet. So you need a good single qubit addressing. So it's not just enough, like I showed you with the 2 blockaded atoms, to put 2 atoms next to each other and do this gate. In the end, you want to have maybe a large grid and do a 2-qubit gate here, here, and here, single qubit gate. You can think of it like you have this laser light show on the atoms, and everything has to work at high fidelity. And also, what is still maybe, what could be better readout is needed. And what do I mean by that? We only briefly talked about the measurements, and I told you the typical measurement is actually you kick all the atoms out in one state, and then you just read out what is left. If you want to do quantum computing, and in particular, if you want to do error correction, you don't always want to kick your atoms out. You want to perform a readout, and then actually keep most of your processor coherent, and then with that readout perform correction operation, or just keep track of those readout results to perform error correction. So we need really good readout that doesn't destroy the qubits, and also, but on all of these fronts, there's a lot of progress, and that's kind of also what my group is working on, having really good readout that doesn't destroy the atoms, and that can be used for quantum error correction. All right, this was just my very short spiel on quantum computing. Now I want to go into quantum simulation, but do you have any questions on that? Yes. Yeah, I think, I mean, of course, there are many possible error correcting codes, but I do like to think, I don't know, that you maybe try to realize some surface code. And okay, surface code, you have your syndrome qubits or your auxiliary qubits, and you have your data qubits. And here you have your auxiliary qubits. And then, okay, what you do is basically you perform pairwise 2-qubit gates here. You could perform this C phase gate. and then you measure stabilizers by reading out this in the middle. So this is what I would have in mind, and then, okay, with this stabilizers, you get syndromes, and then you can, depending on what your strategy is, either just keep track of these syndromes or try to correct them in real time. Yes. Yeah, that's bad. So here, this is here's exactly the challenge. Is you want to measure this guy here? You want to perform a measurement, but you want to leave all the other things untouched. And okay, there are multiple ways of doing that. I'm just gonna pitch my way, or we do this. We use 2 different atoms actually for this. So we use one atom in the middle that has completely different optical transitions that we can read out without touching the other ones. Still, even in a dual species geometry, if I excite them to Rydberg states, I can perform these gates. I can potentially even perform all these gates at the same time. So I have a massive multi-qubit gate, and then I just read out all the squares. And those I can actually, I believe, read out at once. Yeah. So that's what I'm imagining, but other people have other ideas. And there are many ideas. You can get really creative. And one really cool result, also from Harvard, was that you can actually move these atoms around and keep them coherent. So you could even imagine maybe taking these atoms now out somewhere far away and read them out over here. But okay, there are some challenges with that too, I think. Right. Any other questions? Okay, now, okay, we get away from single atoms on 2 atoms. Let's go to more atoms, and then it gets interesting. 3. So now we talk about, it's exactly the same tools. That's what I love actually about these experiments. You don't even have to, I'm always indecisive. I can't decide, do I want to do quantum computing, quantum error correction, or do I want to do many-body physics? You don't have to decide in these experiments. You can do both. And actually, I think exactly in between is where there's a lot of really exciting things. So for me, it's not black or white quantum computing or simulation. It's actually kind of a gray scale, and the 2 things are super related. So, but just to put a label on it, let's call it quantum simulation or call it quantum many-body physics. And the situation is now, okay, we don't just want to think of a single qubit or single spin, but now we put our rearrangement atoms in some grid. Could be 1D, could be 2D, in principle it can be 3D. And then all we do is we shine in a laser beam, our Rydberg thing, Rydberg light, and okay, the 2 knobs that we have is the intensity of the laser, so our Rabi frequency and our detuning. And we will see that these 2 knobs already give rise to a lot. And when I say 1 laser beam, it could be 2 laser beams, but it could be that we have like very large detuning from this intermediate state. So I can really just think about this system, each individual atom. We are now in this number 1 encoding. So we just have the ground state. The ground state couples to the Rydberg state. And we are allowing ourselves also not just to drive on resonance, but also to have some detuning here. So we have some omega and detuning. It's actually a very, very simple situation. And I can write down the Hamiltonian for this. And maybe let me normalize it by h bar. So the Hamiltonian is, okay, I have several atoms. I'm driving each atom just from the ground to the Rydberg state. I can write this as a Pauli matrix, sigma x. So sigma x just 0, 1, 1, 0. So this is exactly Rabi oscillations, basically between the ground and the Rydberg state. However, in this rotating frame, and the Rydberg state is detuned. So here I have an n, or can be detuned if I have some detuning on this. And let me define what n is. Ni is just the projector of having a Rydberg atom on array side I. So this state, depending on what the detuning is has a different energy. Before we were just saying we drive two atoms resonantly, so we didn't have this detuning term. Now we have this detuning term just to stay more general. And then the interesting stuff comes. This is just like two-level system Rabi oscillation where you allow yourself to also have some detuning. But now, of course, we also have interactions. So now we have two body terms. We have Vij, this is our Rydberg interaction, and only the Rydberg states interact, so I have here Ni, Nj. So this is the Hamiltonian. Okay, Ni is just the projector on Rydberg state. Sigma x is just ground Rydberg plus Rydberg ground. So this is just, I mean, if you wanted to write a 2x2 matrix, just driving. And now, okay, we didn't say what Vij is, but okay, we know what Vij is. So typically, because we couple to the same Rydberg state, think about the 100s state, typically now we are in this van der Waals regime where this Vij is just my C6 coefficient over Rij to the 6th power. And now it really depends on how close do you put the atoms, what the exact value of Ij is. Okay, good. So this Hamiltonian actually is a Hamiltonian you know well, I think. And you realize that you know this Hamiltonian well is by realizing that this N, this projector that we had, N is actually related to is basically sigma z. So it's just identity minus sigma z. Okay, see you. Okay. So it's just identity minus sigma z. So if I was to fill this in, I would get that this Hamiltonian, I'm just writing it in sigma x and sigma z, it's just omega over 2. Here I'm summing over I, sigma x, plus here I'm summing over I and I get a sigma z term, plus, and then I get, because I had these two n's there and n has half in here, so I get a quarter Vij sigma z Ij. And because I'm replacing here this n with 1 minus sigma z, there's some single body terms that come out of this two things, and this just I can absorb into this sum. I basically get the delta here plus some, okay, I call it B. So you see there's already some connection maybe to magnetic fields with Bi equals to just summing all these Vij's. Okay, this is now, what is this? Hamiltonian? Our favorite Hamiltonian, or maybe? Yeah, it's just an Ising chain, yeah, exactly. It's just a transverse field Ising model. I have my B field in the Z direction, I have a sigma Z term, and I also have the transverse field, the sigma x. So this is a transverse field Ising model. So this is kind of cool. I just put my atoms where I want them. And I shine in this laser, or maybe it's a 2-photon thing, and I've realized Ising chain, or Ising 2D. So this is so my Rydberg array is just an array of interacting spins. And here I'm just saying, okay, let's treat the ground state as my spin down, or your spin up, whatever you like, and my Rydberg state as my spin up. The cool thing is really, okay, now I have these interacting spins. The cool thing is really this model is highly tunable. So we can look at the Hamiltonian, look at all these terms, and basically we can control them all. So Vij, we control Vij by choosing initially a choice of which Rydberg state we work with. Do we work with the 80s or 100s, plus the geometry of the array. We already saw that before when I showed you the blockaded Rabi oscillation. We actually didn't change the Rydberg state, we just put the atoms closer or further away. So these are the knobs on that. The omega is just your laser power. And the cool thing about this is you don't even have to choose just one power. You can actually do sweeps on this. So actually this omega becomes an omega of t. In your experiment, you can do all kinds of crazy ramps or just quench your system on resonance and then switch it off or sweep it in some way. And the same is true for a delta. This is your laser detuning. And this is also a delta of t, so you can change that. Okay, so we have these knobs. We have an Ising chain, or maybe 2D. So now you can ask, okay, what is the phase diagram? So can we think about which phases we should have? And we now, of course, look at this phase diagram independence of the parameters. So here we could have detuning. This is basically delta, and we're going to normalize it over omega. And in the other one, we have interaction. Okay, so let's, I'm just briefly scrolling back up to the Hamiltonian. Actually, okay, I think the connection to Ising model is nice. For me, maybe as an experimentalist also, I always like to think of this Hamiltonian. I mean, it's only replacing the n's with sigma z's, but actually you see, I think, a more intuitive picture here. And what I first want to focus on, what is actually the role of this delta here? The delta basically tells you how much energy does it cost to put a Rydberg atom on the array. So it's just an energy penalty. If I'm at positive delta, this term is negative. So actually a lower state is when I put all the atoms in Rydberg states. And if I'm at negative delta, okay, this term is positive. And okay, then states that have Rydberg occupation have higher energy. So that's why when I'm here looking at this phase diagram.
I have a question on this.
Okay, cool.
So about the quantum simulation tree, usually I see experiments on Rydberg atoms with two lasers.
Mm-hmm.
One to excite to one state and another one to drive the Rydberg states, okay?
To drive the what, sorry?
Sorry?
One to
For example, one to go to this 5S to 6P, and another one to drive the 6P to Rydberg states. And how does this look in the simulation? I think inside the delta, maybe in the sims, a single frequency of excitation is used. I don't know.
Yeah, so when I changed the delta, okay, again, I kind of simplified. I treated these two lasers as like one, just like one combined omega, but you're asking a great question. What do you actually do in the experiment? So in the experiment, we typically, because here this delta has a very large influence on our Rabi frequency. So in the experiment, we normally keep this frequency fixed. So this is always here. So then this delta is fixed. And then what we do is we take this second leg and the second leg is where we put our delta or our detuning. So when I say, okay, and I'm sorry, there are a lot of deltas. This is the 2 photon. This is the detuning of my simulation. Then I'm just doing the detuning on one of the laser beams, and
Thanks.
typically the upper one. Okay, so this is the knob we are playing now. So it's the frequency of this laser. But we said, okay, it looks like a chemical potential. If I have negative detuning, actually cost energies to put Rydberg atoms on my chain or on my array. So what you would see is here, the phase is just all the atoms, they're pointing down. So this is just all the atoms in the ground state. This is actually where they like to be. If the atoms were not interacting, so let's say over here, all the atoms would be pointing up. If I now sweep the detuning to positive detuning, I can lower my energy by putting Rydberg atoms on the chain. Okay, this is not really interesting yet, and maybe you shouldn't even call it phases because it's just non-interacting atoms. The real interesting thing is as we now go up in this direction, so as we increase the interaction, and my picture I have in my mind, I think about Rydberg blockade. So increasing the interaction, you can think about increasing the blockade radius. So I start to increase it, non-interacting atoms, and now suddenly neighboring atoms are blockaded. So what that means is that it's impossible to put 2 neighboring atoms into a Rydberg state. So now I'm getting a phase here where, okay, I have a ground, Rydberg, I forgot, spin down is ground and up is Rydberg. So I have ground, Rydberg, so ground, Rydberg, and so on. So this is in spin language just an antiferromagnetic phase. And then, okay, if I go higher, think of the blockade radius. Now suddenly I could be in a situation where 3 atoms in this chain are blockaded. So then the phase would look like ground, Rydberg, no, would look like Rydberg, and then I have to have 2 grounds, Rydberg, 2 grounds. So this is not an antiferromagnet. People call this maybe a Z3 ordered phase, depending on which symmetry you are breaking, and you can continue like that. As you increase the blockade radius, you realize different phases. So this is now pretty cool. So in this phase, we just have nearest neighbor blockade. Here we have next nearest neighbor blockade, and so on. And okay, it's nice to realize there's a phase diagram. The question is, can we explore this phase diagram? So can we kind of navigate around there? And this is now very different from maybe degenerate gases. What often you have like in these maybe tunneling lattice experiments is that you just try to prepare the ground state. Like you somehow try to cool it into the ground state and then realize the phase. Here we follow a little bit different recipe. So our preparation, okay, number 1 is we choose our geometry. That's something the lattices can't do. They can't choose a different lattice constant. It's always the same. Here we can choose, okay, where do we want this interaction strength to be? Do we want to sit here or here or here? Basically, this is just putting the atoms closer or further away. And then number 2, we start in a state that we can initialize very nicely. And this is using this optical pumping, the optical selection rules. And for us, the state that is easiest to access is just everything down. Atoms, basically, they like to be in the ground state. If I don't switch on any lasers and so on, they just sit out, hang out there. And okay, now you know more. The ground state, actually, we have all these many levels. But using optical pumping, so these optical selection rules, I can just prepare one of those ground state levels and everything sits down. And then number 3 is, okay, we switch on our Rydberg laser And now, okay, we use the fact that we can actually dynamically change the omega and the detuning. So what we actually, if I look at the phase diagram, what we would like to do, okay, we choose our geometry. Let's say we choose maybe here our point here. The atoms start all pointing down, and then we want to take the system on a trajectory, and we want to sweep into this new phase. What does that mean for our lasers? Well, for our lasers, it just means we do the following. Okay, the two knobs we have on the laser is our intensity, our Rabi frequency, and our detuning. And okay, for the detuning, maybe here's 0. The detuning we take, first we switch on the laser beam. Okay, we just do this, switch it on, and maybe in the end we switch it off again. And as we do that, we first have our detuning negative, because this is in the phase where all the spins are pointing down, and then we sweep it upwards, and as we sweep it upwards, and it could be linear ramp or it could be some other ramp, we are taking now the system here from the left to the right. And okay, here, what is important for slow ramps, what we are doing an adiabatic preparation of the desired phase. So we start in a state that is easy to prepare, all atoms pointing down, and then we take, with the laser, we take the system on a trajectory, and if we do it sufficiently slowly, we get here, for example, into this antiferromagnetic phase. And this is literally what you do in the experiment. So once you have set up, you're only sitting there on the computer, you choose your geometry, and you choose your ramp. And by now, there are even companies that offer this on the cloud. So you can actually, as a web service with Amazon, you can program these sequences on atom arrays. And then, okay, after we did that, number 4, okay, we still want to measure. So then we measure, and we see which atom went into a Rydberg state and which one is left. Okay, let's, because this is kind of cool. Okay, here are lots of gates that I kind of skipped, many different gates, but this is what I wanted to show. So this is exactly these 4 steps in an experiment. So this is, let's look at the bottom here. At the bottom here, these are 13 atoms. 13 atoms there, we picked the geometry, we put them at this spacing. Here the spacing is chosen that for this given Rydberg state, we only would have nearest neighbor blockade. And here, now what we're doing in time is we are sweeping this detuning. We switch on the laser beam and take the detuning from negative to positive. You see, as you take it to positive, the system wants to put Rydberg states in it, but okay, the Rydberg states, they also interact, so they can't be next to each other. So this is exactly what you find here. And this is how you take the data. You just take an image, and these Rydberg atoms actually at the end of the experiment, they kind of fly away, so they get lost. And then we just take an image and we identify which atom got lost, and we call this a Rydberg atom. And then you see how this stripe phase, this antiferromagnet, appears on the array. And then you do exactly the same experiment, but you put the atoms closer to each other, and then you get Rydberg, ground, ground, Rydberg, ground, ground, or up, down, down, up, down, down. This Z3 ordered phase, and here you get the Z4 ordered phase. So it's highly programmable. Just to show you, I also did the homework, so this is the homework. This morning I did the homework. Yeah, so this is highly programmable, and you can use it to study phase transitions. Study phase transitions. And okay, here what we kind of try to do is, okay, we just want to prepare the phase. So we try to go slowly and see what happens, but nobody tells you you have to go slowly. And actually, I think here in the workshop you want to go, or in the summer school you want to go non-slowly, so you can also use this to study non-equilibrium physics. So you could, for example, say, okay, what happens if I don't go slowly into this new phase, but if I go too fast? What will happen is actually, okay, I'm not preparing exactly the antiferromagnetic state, but I will have some defects, so-called domain walls, between maybe some ordered patches, and the physics that describes, I don't know, how many domain walls you have and how that scales with your speed. Maybe you know about this. You can study, for example, the Kibble-Zurek physics, which is this looking at the domain wall scaling.
Hannes.
Yeah.
Here just 15 minutes to the end.
15 minutes, yeah. No, that's good, that's good. And my goal is really here to just show you what are your knobs, and then I think the next generation of experiments is what you will come up with, and then we program it on the machine. So here we can study the scaling of the domain walls. You can study quench dynamics. And I think also yesterday somebody asked Jamir in his talk about like quantum many-body scars and scar physics. That was actually kind of discovered when we were playing around just with these quench dynamics on these systems. We saw, ooh, there's very interesting dynamics appearing, and then more clever people came up with a whole framework of many-body scars. And then here also, for me, always quantum many-body physics and quantum computing is kind of so related, because I can also use this same thing for state preparation. So in this antiferromagnetic state, actually, if you look at this, why is it actually down, up, down, up, down, up? Why is it not up, down, up, down, up, down? Here, actually, in this example, we've chosen exactly kind of a configuration that favors one antiferromagnetic state over the other one. It's basically the number of atoms, and that this atom at the edge likes to sit first in a Rydberg state because it doesn't have any neighbor to the right side to interact with. So this kind of pins this state, but you can actually get rid of this pinning and make up, down, completely degenerate with down, up, down, up. So you can very easily with these sweeps actually prepare entangled states that then look like this, plus all the other way around. And that's, I would say, maybe the easiest way to make a large GHZ state. Simply by changing here this laser detuning and sweeping into this degenerate antiferromagnetic state. And this, for example, was a paper by Omran. Yeah. Yeah. It's very snapshot, basically. Yeah. So you can decide. Also, this is kind of what we do here. We do the sweep up to a given point, like here, and then we take a snapshot. Or we take the sweep a little further and then take a snapshot, and that's kind of how we populate this whole 2D thing. And that's also like, if I quench this system, I can decide, do I quench it for half a microsecond or 600 nanoseconds, and I can stop it for all those times and then take a snapshot. And that's how I, for example, see these oscillations of the quantum many-body scars. Yeah, I have. In the end, it comes down to very precise control of the laser. Yeah.
So it relies on the fact that like we have like the Z2, Z3, Z4 sort of translation symmetry. And then like without choosing a particular symmetry sector, you might just have like this generic state, which will be at equal superposition. But then like, isn't it just limited to then having those GHZ states like, well, which will be, you know, like those, okay, because I see like how you can have like Z2, which will just have like 2 components and so. But for instance, if we had like, if we wanted to have like, I don't know, Z8 or Z10, then like that thing would be already hard, right? Because like you need to have like a very large Rydberg blockade, right? And
yes, that would be maybe harder, but okay, I could have a larger Rydberg blockade. And actually, I think, okay, this was 2017, 18, 19. We played with 1D going 2D. Now many more atoms can be blockaded. So, those things I would more think about in 2D maybe.
And okay, and maybe a slightly broader question, like those systems are having long-range interactions, right? Like this.
It depends on what you call long-range interaction, and I think you can get serious arguments with theoreticians, with you, for instance. I'm perfectly fine calling it long-range interaction because for me, like, these are micrometers, but the scaling is like, yeah. So it's not long-range in kind of a strict sense, yeah. I like to call it strong interactions.
Okay, but pragmatically, regarding of, well, maybe ignoring like philosophical differences, like those things do matter if it comes to the ordering of like certain phases, for instance, right? Like if you increase the Rydberg blockade, then like there will be different phases, well, different phase diagrams depending on if you include those, you know, like long-range tails.
Yeah, exactly. Yeah. This is kind of the intuitive story I'm giving here. Actually, only uses blockade, but you are right. These longer range tails, they matter a lot. They also tell you, can you actually reach these phases or so? Those are really important. But those get much harder to simulate, and yeah.
And there is no equivalent of like some kind of a screening for those interactions, right? Like if we had like Coulomb interactions, then for instance, those ones in solid state would get screened, right? But in here, there's like no kind of, I don't know.
Yeah,
like
I don't really know how to think about it, but I mean, in some sense, maybe blockade looks almost like screening. I don't know, but yeah. Okay, but maybe let me continue because we only have like 7 minutes.
Sure.
Yeah. I just, but okay, the most important thing is here, I want to show you what are the knobs. I want to show you, okay, we can explore both equilibrium, non-equilibrium dynamics. And then now this really led to an explosion. Of course, this was just 1D. Here you see 2D. So this is now 2021. And this is a very nice example from Antoine Brevet's, very similar example also from Harvard around that time. So this is now really kind of, now we are reaching the present time. But here, okay, in this example, also they just, for example, looked at this antiferromagnetic situation. And you can see, I mean, it's incredible how they get this ordered state here with 200 atoms. And that's pretty incredible. But then, okay, now you get a little bit greedy also. Okay, now a square lattice or square array, just by simply programming a different geometry, okay, maybe I can put them here into a triangular lattice. So now you can ask your question, okay, what happens in a triangular lattice, so beyond square? Geometries. You could, for example, have a triangular lattice. And okay, there people then think about, okay, can I have a frustrated system where simply you would arrange them maybe in this antiferromagnetic regime, but on a triangle, okay, where now this last guy has to decide, am I pointing up or down? And in the end, okay, maybe your ground state has a lot of degeneracies because of this frustration. This is one example. Another very famous example now. You could put the atoms on a Kagome lattice. And okay, now I'm going pretty fast, but this is all just to kind of highlight what actually still it's exactly the same knobs. It's just ground to Rydberg and I have this detuning, and I have this omega. And now just by changing geometry, I explore frustration. In this Kagome lattice, actually a very recent highlight, which was really cool. Was kind of the exploration of topological spin liquids. Topological spin liquids. And this was by Semeghini, 2021 Science. So here also the atoms were just on a Kagome lattice, and by picking the right blockade radius, they realized this highly degenerate state that had some properties of a topological spin liquid. And okay, I'm not going to explain topological spin liquids. I would also not be the most qualified person for that, but I kind of want to point you towards, okay, it's actually much more than what you would just come up with transverse field Ising model. You would think, oh, probably you go run out of steam pretty quickly. But okay, this is really kind of the time for also theoreticians to be then creative and realize different mappings. For example, this transverse field Ising model was then kind of mapped onto a dimer model that was realizing this spin liquid physics. And then cool is also, okay, this is all spin models, but there are also connections to optimization problems. This got a lot of people excited, and I'm just doing name dropping here. So this is maximum independent set. This is a NP hard problem, and this is very nicely analyzed by Hannes Pichler on a paper that's, I think, still just on the archive, 2018. And then what is that? What is the independent set? Basically, given a graph, okay, so I have some vortices, edges, and these are connected. I want to find how can I color this graph. How can I color these vortices without these colored vortices sharing a connection? And okay, now I can ask, what is the largest set? What is the largest kind of possible number of vortices I can color? And you can already see there seems to be some connection maybe to Rydberg. I could maybe arrange atoms in a way that these edges here exactly are maybe the blockade, so I cannot excite two atoms in a Rydberg state if there's an edge in between. And now I can actually use the exactly the same framework to now realize and explore, okay, can I find these maximum independent sets? And yeah, the cool thing is it's exactly the same knobs, detuning, omega, like exploring phase transitions, exploring non-equilibrium dynamics, exploring here this maximum independent set. And there's a cool experiment. And with that, we are basically at the present day. This was by SEPA, and this is Science 2022. And with that, okay, I still have a lot on topological models and so on, but maybe here's a good time to finish. Thanks.
Okay. So I think Hannes did something fundamental for the school, because this field makes sense only out of experiments, so it's very different than some older approach to theoretical physics when people like to write down stuff and solve them. So the presence of someone like Hannes, I think, gave deep meaning to what we would like to convey. So before lunch, are there any last urgent questions? I will take like maximum 1 or 2 urgent, because we have very tight time. We have to reconvene at 2 today. Good. In the sake of making the entire schedule flow, if there are no extra questions, I would thank Hannes again